Welcome back everybody after lunch. I hope you're sated and very pleased to start this afternoon's session by inviting Helmut Maier to talk to us about the recent results on gas.
Thank you for the introduction. First, I want to thank the organizers for the invitation. This has been one of the work really good in conference for Professor Alladi. I want to talk on joint work with Michael Rassias. I have been working with Michael for a few years. He's a very active young researcher. He only relatively recently completed his PhD. His advisor is Helmut. So first the statement of the result that we then really find. I actually wanted to use the laser point, so it seems to be a problem. If I press here, it does Yeah. So this is interesting. Often people that constant times dysfunction. Remarkable is that there is only the first power of the people, the denominator. This already was the topic in this morning in the talk of Professor Baker. This is the spectacular recent improvement from 5 authors. They were also mentioned by Professor Baker, Kevin Cork, Ben Green, Terence Tao, Roger B. Brown, and James Maynard. Now, in addition, we want to prove that the interval Pn plus 1 also should contain the cave power of a prime number. Now, all results on large gaps are based on the average ranking method. In its simplest form, one constructs an interval M0, M0 plus 1 by a sequence of sieving steps. One partitions the interval into 5 subintervals and takes the set of primes which lie in these intervals, and for each set one imposes congruences. For the first and the third interval, one always requests divisibility, whereas for the other intervals there is some variation in the different versions. Now, if U satisfies any of the congruences, equal minus CP, for the CPs defined in this set here, then it follows that M0 plus U is composite. That means it is not a prime number. If the congruences from the previous sheet to cover the entire interval, then the interval m0 plus y contain only composite numbers, and that Pn be the prime number, the largest prime number less than m0, Pn plus 1 the smallest big m0 plus y, then Pn plus 1 minus Pn is at least y. Now let us return to the first or the third set of congruences. These congruences enforce that the set of survivors, we speak of survivors if some a number doesn't satisfy any of these congruences, then one can easily show that this survival set consists only essentially of the prime numbers and a small set consisting of smooth numbers, and this residual set is very small. Now S is then further reduced by congruences, and also this set was already, the notation for this set was already there in the talk of Professor Baker. We call it S of A, where A has the components AP1 to APL2, the numbers which show up in these congruences. Now in the original application of the Erdős-Reinke method, these choices were fairly simple. One applied the so-called C of J was applied. One always strikes out the biggest residue class. Now the key to the improvement is that these choices are done in a much more sophisticated manner. The last sealing step is especially remarkable. U congruent minus P4 P4. In this sealing step, the survivors of the first three sealing steps are eliminated. And in the previous versions, one congruence removed one survivor in the Erdős-Reinke method. The first improvement was obtained in joint work of Karl Pomerantz and myself. A sealing step removes 1 to 2 survivors. Already there were some doses of combinatorics and graph theory. One considered the residue classes as edges, the survivors as vertices of the graph. Finally, Janos Prinz could remove 2 survivors. But all these innovations only led to an improvement of the constant C in this result. G1 of n is this function. In the future I will refer to a G1 result, a result in which this function shows up, and I will also talk of the G1 method. The G2 function is bigger by a factor of 3n, so the square here is removed. The G2 result is that Pn plus 1 minus Pn is larger than or equal to C times G2 of n infinitely often. Now, crucial for the G2 method is the last sealing step. In the last sealing step, one congruence removes C of x survivors, where this number tends to infinity, as x tends to infinity. All this has been done in this quintuple paper. I also will call this the quintuple paper. Kevin Ford, Jim Green, Sergei Konyakin, James Miller, Terence Hall. Now our result will closely follow the ideas of these quintuple papers. It will be contained with some new ingredients and also with some older ideas.
Can you remind us what was known 20 years ago?
20 years ago there was this G1 result. That was actually known, that was known until 2 years ago, I think. Yeah. So this improvement is relatively recent.
So you only reduce the second half?
So G1 of n is this function with the square of the log 3n. That was until recently all what was known for the gaps between prime numbers. And since December 2015, there was some larger function known by a subset of three of the authors. And G2 of n is only, as far as I know, on the archive since April 2015.
So the non-expert is not that impressive, but I guess
So,
if you're in the next one.
yeah, but it's the...
How much did Erdős offer?
Yeah, others offer $10,000 for the improvement of this result here. And it stood probably for 70 years. It was not.
That's an impressive technical feat.
Yeah.
That's all the knowledge to decide whether the C can be made arbitrarily large.
Yeah. Now we use some combination of the shrinking method with the matrix method. The matrix method was introduced by the speaker in 1991. The purpose was to find chains of large gaps between consecutive primes. The matrix contains translates of a base row, and the base row is the row we considered previously. That was M0 was determined by these congruences, and M0, the interval from M0 plus 1 to M0 plus 1. In the first version would only contain composite numbers. In some versions it will contain only very few prime numbers. In this version one needs some prime numbers to get the primes between the chains must lie. Then one considers the translates. The columns of the matrix are arithmetic progressions. P of x, I did not write that here is the product of all the primes less than x. This is the matrix one considers. Then one counts the number of the primes in that matrix in two ways. One counts per column by applying results on primes in arithmetic progressions, and then some of the rows must contain the desired configuration. Now the result I want to talk about has also a precursor, namely a triple paper of Ford, Konyakin, and found large gaps between consecutive prime numbers containing perfect powers. The matrix method is in in some sense already present there. And then we had a G1, Michael and I had a G1 result with the old function in which there is still a square of the tau in the denominator, which combines, which also uses the matrix method. How does the matrix look like? The matrix now consists of the base row, and the base row looks like this with R equals 0. It has the cave power of m0 plus 1 as the initial point, and then it has it consists of very few prime numbers. Most of the numbers are composite. One wants the interval between these prime numbers contain cave powers of primes. These can be found in the first column. That's by applying theorems about primes in arithmetic progressions. Okay, one takes again these seeding steps. We call the survivors S of A and S of B. And now there is a new condition. I want to call that in the sequel the cave power, the red cave power condition. We do not always print it in red. So the fact that there is a cave prime powers in that interval enforces that we have to consider only these residue classes for which these congruences have a solution. The G1 result with the square in the denominator is again fairly easy. One does not need much effort to construct the vectors A and B. M0 plus 1 indicates an appropriate interval of the base row. Since if U is congruent in S, then this number in the R row is congruent 0 mod S. That means these integers do not survive the seeding steps. Now the G2 result then is what I want to talk about. And it consists, as I already told you, in a modification of the ideas of the two Table papers, and of course also the ideas of the precursors. The earliest precursors can be seen as Boltzmann, Pins, and Yildirim. In this G2 result, A and B are found by randomization, and in the last seeding step U congruent minus BP, one congruence removes many survivors. The solution sets of these congruences are viewed as edges EP of the hypergraph Q. That means in the seeding steps entire edges are removed, and one wants, of course, that they, after these edges have been removed, only very few vertices are left. Now, there have been combinatorialists who were working on the results needed. The hypergraph covering theorem, the names are mainly related, this result is mainly related to the names Finkelstein and Spencer, and also Wojtek Riddle. if the edges of a hypergraph have suitable properties, and if we have a probability measure on the set of edges with suitable properties, then the hypergraph can be covered by a union of edges with only a very small residual set. The probability measure needed is constructed by the use of sequoids, which are due to James Maynard. They occur in his paper dense cluster of primes in subsets. Now this hypergraph covering the site cannot be used in the original manner. It must be somehow modified, since not all edges have the same cardinality. The request is that the edges are not too large. Each CV step is sparse. Very small co-degrees, degree bound, and I do not want to go on the details. Not in any way is the field used. And the theorem we want to prove will be reduced to the following result, that x be sufficiently large. Then there is a quantity C, and there is a way to consider random vectors. These congruence classes became random variables, and they are now restricted to A and B. These are the sets which satisfy the red cave power condition. So these conclusions are also all contained in the quintuple paper. An element A is called good if it satisfies these conditions about the cardinality of the edges. Now, theorem 0.5 is again established by a probabilistic argument with a weight function which is closely modeled to the weight function in the quintuple paper. The restrictions A of A, E from B, that is the red cave power condition, bring some additional complications. The function W, P, N will be different from 0 only if N belongs to a set G of P of so-called P good integers. The definition of G of P is based on the set G of integers. When is an integer called good? Now we have to return to the we have to make an excursion on the theory of cave power residues. If a number is a cave power residue, then the congruence x to the k to 1n has this number of solution, and we introduce then this number. This is we now take a number and ask for how many prime numbers S is the red cave power condition satisfied. This is the expected value, and we compare this with the actual value. And we show them that for most n, the value of R n is close to its average, R star of u. Whenever this is satisfied, we call the number n a good integer, otherwise bad integer. We then make this definition of G, the deviation from the expected number should be at most log x to the minus 1 over 14. And then we will introduce, we will have to do with admissible R-tuples. G of P is the set of all n, for which not only n, but also these numbers with this are good. So the one new ingredient in comparison to the quintuple table is within this components condition that take our condition. Now we have to one has to construct a good C. They then can apply to the hypergraph covering theorem and in the result. So this is what's new to the tuple paper, also especially to the paper of James Maynard, dense clusters of primes. So this function has to be constructed. Now, all the conditions for 44.7 are already found in the quintuple paper. The new ingredient in our paper is that the weight function should be concentrated on the functions, on the integers which satisfy the Redcliffe power condition, and also there should be in G of P. Okay, then one has this uniformity, the sums should be independent from the prime number P, and also results of the behavior in arithmetic progressions. Now, an important piece of the theorem is a correlation inequality. One wants to show that the events in I is from S of A are asymptotically independent. So the probability that a single in I is from SA is sigma, and if there are T such events, the probability should be the product sigma to the T. And the proof of this result is easier in the quintuple paper, since there the vectors A, when we take it from a simple set, they need not to satisfy the power condition. Okay, we have to take that into account, and that makes the proof somewhat more complicated. We compute the probability by the classical Laplace definition of the probability. Number of favorable cases divided, which are given by this sum divided by number of possible cases, but we can then obtain asymptotic independence of these events. Now, one then introduces a probability measure by these definitions here. And the random vectors LP are determined by conditional probabilities. So under the condition that the random vector assumes the value A, this lemma also because in favor of Maynard. For the proof, we follow the lines of the book of Watt of the quintuple paper. And now the modification of the weight function. So first of all, we need the definition of Maynard. There the weights depend from a collection of linear forms. So we have a collection of linear forms, Li of any string I n plus Di, and L should be admissible, but means they do not have a fixed prime divisor. Here. These are the weights from Maynard. They contain these vectors which originally come from the Seilberg-Ziel, and the whole treatment is an extension of the Goldstone, Pins and Yildirim method on the small gaps between prime numbers. Okay, so these weights already occur in a somewhat simpler form, probably the linear forms there are just from the form n plus hi, appear in the papers of Goldstone, Pins and Yildirim. Okay, these are the results of Maynard. And now again the variation, we introduce W star of n, Pn, which is only different from 0 if this correct case powerful ones is solvable. And the solvability of this has will be checked by the use of Dirichlet characters. So there is a Dirichlet character such that the sum is 1 if and only if this function is solvable, 0 otherwise. And with this we can then prove the same asymptotic as in the quintuple paper. If by the introduction of these Dirichlet characters one is led to the problem for estimating sums over Dirichlet characters which are taken over shifted prime numbers, and we found that the result of Friedland, Fong and Sparlinski is suitable. It might be also other these previous results might do the job. Okay, and then the final choice is that we is Lysian for the weight. And we still have to conclude the proof. We have to estimate the error, which comes from the n which are not in G of P. And this is done by applying certain Chebyshev type estimates. We estimate the moments in probability theory that would be called the variance of that random variable. One can expand the square and this will lead to moments, and the moments are estimated here. And here is one example how one estimates the moments, one changes order of summation, and this one is led to these sums in which the power conference condition, safe power condition is obtained here. One changes order of summation and has led to a look at a sum like this. Now these weights show only small variations with respect to many parameters. They depend on many parameters, but they are not very insensitive to the change of these parameters. Okay, and that finally concludes the proof of our theory. So, thank you for the attention.
Well, thank you very much, Helmut. We are a bit short of time, so I suggest if you have any questions, you can call Helmut later, and we should carry on straight away with the next talk.
Yeah.